Bismillahirrahmanirrahim. I am Professor Jamil. You are watching my YouTube channel, and today we are having lecture number 2 on gamma function, and we shall do a relation for the gamma function which is known as recurrence relation. And let's do this relation in the form of a question. This is known as fundamental recurrence relation, and this relation may appear in the form of a question. So let's write statement of the question. Derive the fundamental recurrence relation gamma z plus 1 is equal to z into gamma z using Euler's infinite limit for the gamma function. This is a statement of the question. Also, proof from this relation that gamma of z plus 1 is z factorial. You need to prove this relation. Name of this relation is fundamental recurrence relation, and you need to derive this relation. How you need to derive it? By using the Euler's infinite limit for the gamma function. There are different definitions for the gamma function, and out of those three different definitions, you have been restricted in the question that you will use Euler's infinite limit for the gamma function. When you have derived this relation, then you need to do another job, and that is gamma z plus 1 is z factorial. Right? Now, recurrence is a word which is from recur. Recur means to happen again. So, what is happening again here? Here is a gamma function whose argument is z plus 1, and the gamma function is occurring again on the other side with different argument z. So, gamma function is occurring two times, mean gamma function here, and it is reoccurring here on the right hand side. It is for this reason that this kind of relation is known as a recurrence relation, and since this relation has a gamma function, and it is known as recurrence relation for the gamma function. So let's start solution of this problem. And for this relation, we need to have in our mind the definition due to Euler. And that definition due to Euler is in the form of infinite limit. So let's start the solution. Let's start solution on the other board. So here is your solution, or you can say your proof. Keep it before you. Euler's infinite limit. So start from here. We know that Euler's infinite limit form for gamma function is, so first write the definition of the gamma function, and that is limit n approaches to infinity, and for n you have n factors in the numerator and n plus 1 factors in the denominator in the form of z into z plus 1 into z plus 2 dot dot z plus n, and whole thing is multiplied with n to the power z. Now, according to the relation, you need gamma z plus 1. How can you achieve it? Replace everywhere in this equation z by z plus 1. So let's do this. Name it as an equation number 1. You might be in need of using it again somewhere in the solution. So this is equation number 1. So replace z by z plus 1 in equation 1. Gamma z plus 1 limit n approaches to infinity. There is no z in the numerator within the square brackets, so write this everything same as before over z is to be replaced with z plus 1. So this z will become z plus 1, and when you replace z by z plus 1, this plus 1 will make z plus 2. Z plus 1 here plus 2 will make z plus 3 dot dot, and this is z plus 1 plus n, and here n to the power, this z will be replaced with z plus 1. So everywhere in the equation number 1, z has been replaced by z plus 1. Now, as you need on the other side gamma z again, it means you can simplify this relation so that you get this very same expression over here. How can you do this? 1 to n factors are same, they will be kept same, and limit will be written again because n is same, it has not been altered in any way, dot dot n, and in the denominator the factors in z start from z. There is no z here. You can multiply and divide by z. So in the first step I have divided by z, mean multiplied with z in the denominator, z, and the next factors are same, z plus 2 plus 3 dot dot. You have z plus n, and these three dots mean there are lot of hidden factors over here. So as you move left, z plus 3 for example, and on its left you have z plus 2. So 1 is subtracted from this factor to get z plus 2. 3 minus 1 will be 2. 1 subtracted again will give you z plus 1. So from this factor, if you need the previous factor, that will be obtained by subtracting 1 from here. And 1 subtracted means you will have z plus n. So here is z plus n and z plus 1 plus n. N to the power z and n to the power 1. Now, if you look carefully, you have this part, and this. This is same. Everything is multiplying together. This is same as in equation number 1. So group together all these and keep and separate the other factors. What are the other factors? So blue, 1, this and this one. So you can set or rearrange in this form. Limit n approaches to infinity, 1 into 2 into 3 dot dot n divided, oh, you divided by z, you should also multiply by z. So z here, you have divided by z and multiplied by z, and you have separated these two exponents into a product, n to the power z and n to the power 1, and you have written one factor preceding to this one. So preceding factor is obtained by reducing the number by 1. So 1 reduced, you will get 1 z plus n here. So 1 to n, so z into z plus 1, z plus 2, absorb this factor into the so on, mean these three dots, dot dot, z plus n, and n to the power z. This is one piece, and other one is limit again, n approaches to infinity, and you have n to the power 1 into z over z plus 1 plus n. You know, when you are finding limit, in limit x approaches to a, fx gx, and this is equal to limit x approaches to a, fx, and into limit x approaches to a, gx. I mean, limit can be distributed on the factors, and in this way this limit n approaches to infinity has been distributed, mean applied on this piece, and since there is also n here and the limit has been separated for this. Imagine that this is all fg, g of z, and this is all f of z, right? Okay, so what is this now? You can use equation number 1 here. This is all gamma z. So using equation number 1, what you will get? Gamma of z plus 1 is equal to gamma of z, for this in the round brackets I put here. And what about this? You need to evaluate this limit. And limit n approaches to infinity, this is the highest power of n is 1, and in the downside highest power of n is also 1. This n can be pulled out like this. Limit n approaches to infinity, n into z, and in the denominator n is taken out, and you have z by n plus 1 by n and plus 1. This n will be cancelled, and you have gamma z into limit n approaches to infinity, z over n plus 1 over n plus 1, and now apply the limit. Gamma z into z over infinity is 0, 1 over infinity is 0, and this is 1. So you have gamma z into z, and on the left you have gamma z plus 1. So you can also write it as gamma z plus 1 equals z on the left and dot gamma z on the right. So this is the relation which you were asked to derive from Euler's infinite limit definition of the gamma function, which we have written in equation number 1. So one piece of the question has been done. Then the recurrence relation has been derived. The other one was, look, the second piece. The second one is, you need to prove from this relation that gamma z plus 1 is z factorial. So let's do this. This is your first answer. And for the second, for gamma z plus 1 equals z factorial, we take gamma z plus 1 equals z gamma z. So you are finding a factorial of something. Use this z values. For z equal to 1, gamma 0 plus 1 will make 1, and 1 into 1, and this gamma 1 is 1. Gamma 1 is 1, so you have 1. Z equal to 2, use this relation again. 2 plus 1 is 3, this is 2, and this is gamma 2. Gamma, 1. Z 1 plus 1, this makes 2. Gamma 2 is this one, because gamma 1 we already know is 1. In lecture number 1 we proved from the definition of Euler in the form of infinite limit that gamma 1 is 1. This has been proved in lecture number 1. If you don't understand this, you should look my lecture number 1 on the gamma function. Now this is gamma 3, this is 2 into gamma 2. Gamma 2 is in the upside, and this is 2 dot, gamma 2 is 1, so it is 1. Now for z equal 3, gamma 3 plus 1 will make 4, and this is 3 gamma 3, and gamma 3 is in the upside, so 3 gamma 3 is 2 into 1, so it is 2 into 1. For z equal to 4, this relation will give you gamma 5, and 4 plus 1 is 5, and here 4 into gamma 4, and 4 dot, gamma 4 is here, and this is 3, 2, 1. Now look, 2 into 1 is 2 factorial, 3 into 1, 2 into 1 is 3 factorial, this is 4 factorial, and so on. Gamma z plus 1 will be, look, if argument of gamma is 3, then the factorial is 2. If argument of gamma is 4, then the factorial is 3. And if argument of gamma is 5, then the factorial is 4, mean 1 less. So if you do this, 1 less, that will be z, and there will be a factorial sign. So by generalizing these, this 1 factorial you understand will be 1 factorial. This 1 is 1 factorial. So to gamma 2 mean 1 factorial, gamma 3 mean 2 factorial, mean 1 less. Gamma 4 mean 3 factorial, 1 less. 4 and 3. So factorial is of a digit which is 1 less than the argument of the gamma function. And gamma 5 mean 4 factorial. So z plus 1 would mean factorial of z, 1 less. So z plus 1 when reduced by 1 will give you z. So this is the proof for gamma z plus 1 equal to z factorial. This is your answer for the second part of the problem, and your problem is finished. This was the solution of this question. Fundamental recurrence relation has been derived, and then this relation has been used for the factorial function, mean gamma z plus 1 is z factorial, and the solution was pretty simple, and I hope this solution should be of some value to you, because this question might have been there in the exam in various universities. And you should also remember this relation by heart. I mean, gamma z plus 1 is z factorial, And this relation, since this is fundamental relation, this is used again and again in many coming problems. So remember this relation also. Thanks for watching. Keep watching for more lectures on gamma function. Thank you.